Hi, I'm Connor Reed. I'm the electrical engineer, and I'm the team lead. This is 22036.
Hi, my name is Vincent Tran. I'm a mechanical engineer and the procurement lead.
I'm Danny Chance, and I'm an optical engineer.
Hi, my name is Michael Higgins, and I'm a mechanical engineer.
The project is sponsored by Tucson Embedded Systems. The proposed solution is to develop a semi-autonomous robot to validate traffic camera tracking using internal tracking abilities and external calibration patterns. The stakeholders are TES, Institute of Automated Mobility, and Arizona Commerce Authority. The outcome of this project will be a semi-autonomous driving, remote control, small-scaled vehicle that will have the ability to accurately track its position in time so that IAM can use that data to validate a visual tracking system to simulate real-world interactions for autonomous vehicle training. This will be important in the development of future autonomous vehicles to ensure the safety of human life within these vehicles and to track how autonomous vehicles and human-driven vehicles interact with each other.
To match the scale performance and dimensions of a road car, a 6-scale off-the-shelf RC car chassis was used. The chassis featured a linkage suspension with springs, front-wheel steering, an electric powertrain, a top speed of 14 miles per hour, and had a modular platform that allowed for modifications. Selecting a functioning chassis reduced the experience risk with integrating and designing a steering and suspension system. Secondly, it also reduced the budget and manufacturing risk for the team as well. The whole cost of the RC chassis was about $1,300, and if self-produced, would take much longer and much more money to machine all the necessary components required. The last reason was that the chassis had good mounting points for a protective roll cage and for electronics mounts as well. Cosmetic items were removed to reduce the weight of the car. A dowel sheet cut with a laser cutter was mounted on top of the support shock towers of the chassis to accommodate additional electronics. The stock wheels on the car were foam-filled, which had poor handling performances at higher speed. Larger 8-inch air-filled electric scooter wheels were substituted. A 3D printed adapter made of ABS plastic was designed to fit into the hex head pattern of the drivetrain. This was designed to handle a maximum of 3 foot-pounds of torque from the motor.
The protective roll cage was designed using SolidWorks weldments. The cage was designed such that at the bottom of the suspension travel, the wheels will not collide with the cage. This was verified using CAD implementation. The width was also designed to fully cover the mounted electronics. Using the weldments toolbox, a cut list was automatically generated in a SolidWorks drawing, which was utilized to cut steel tubing. An inside shadow of the two planes of the roll cage was cut using a laser cutter to make a jig to weld the tubing around to make sure it was straight. The tubes were then welded together to fabricate the roll cage. Tabs were then welded onto the robot frame and the roll cage to be mounted via nuts and bolts. This roll cage was also used to mount various electronics and antennas, so tabs for those electronics were welded on. The calibration pattern is also going to be mounted onto the top of the roll cage.
Our electrical design was based on a Raspberry Pi for our data recorder as well as our main operating CPU. This was chosen because there are many projects that have been done before that were similar to ours, and we could pull as much as we could from those projects. Our robot has several sensors that help to position the robot in its environment. Our robot uses sonar, an IMU, a dead reckoning GPS, and a LiDAR sensor to collect data for the internal positioning. Some of the issues we had developing this electronic system had a lot to do with the supply chain issues, as well as inexperience with designing usable electronics packages. One of the requirements that our sponsor expressed was that all of our electronics needed to be properly grounded and have polarity checks throughout the building of the electronics package. This was because the parts we needed to use were more expensive and unavailable because of the supply chain issues. One of the problems that we ran into was that the GPS breakout board that we used had the ability to use UART, SPI, or I2C. While that sounds like a good thing, for us it was not. Unfortunately, the chip on the breakout board only has one output, and this meant that the UART communications were being put through the SPI lines. Because we were using these lines for another sensor, we had to cut the traces on the GPS breakout board. This allowed us to use SPI for something other than the GPS. Our main motherboard is a hand-soldered breakout board that has connectors for each sensor.
All of the software for the robot was completed with the robot operating system known as ROS. ROS was chosen because it is an open source software with existing packages that served the main needs of our project. The majority of the code was written using C++ and Python, as these languages are most commonly used with the Raspberry Pi and also the languages our team members had the most experience using. We were able to use ROS to have each individual sensor transmit and receive on its own node in order to get the most modularity. ROS needed to be installed on 2 different operating systems so that all of the communication protocols could work successfully. The 2 operating systems we tried using were Ubuntu and Raspbian. Ubuntu was not successful as we could not enable the UART using this operating system. Therefore, Raspbian was the primary operating system used for ROS. One of the main challenges our team faced with the software aspect of the project was the lack of experience. Our team consisted of only 1 electrical and computer engineer with the proper background knowledge, and only 1 other member having some relevant software experience as well. Our sponsor was able to help us overcome this problem by providing us with various resources, as well as having a TES employee with a lot of experience with ROS help us overcome many setbacks.
For this project, the group had a set budget of $4,000. This list displays all the necessary materials and components purchased. With all the items purchased, there is about $950 left of the budget. The system requirements consisted of a few components. The first requirement was to have GPS tracking and the ability to be tracked by traffic cameras. Then the next set of requirements was to collect and transmit kinematic data and GPS data. This was tested using a live demonstration on an intersection, and it passed the test. For customer constraints, a size requirement was set where the product would be no greater than a 3x3x3 foot cube. This was verified in CAD and also with dimensions as well. The next requirement was that the car would not weigh over 70 pounds. This was done by inspection by weighing the assembly and while also adding up the individual weights of the components as well. The car passed this requirement. The next requirement was that the car should survive a 4-foot drop off of a table. This test was performed and the result was the car passed the test. Then finally, a minimum speed requirement of 19 miles per hour was needed. This was tested by attaching a phone with the speedometer app. The result was that with the new wheels, the car could travel at 17 miles per hour. This requirement was not met, and all other customer requirements passed. The interface requirements consisted of system communications. These were wireless protocols such as 802.11. This was tested by demonstration and by verifying that it could perform this function. All of the interface requirements passed. The electrical requirements consisted of those that would ensure the car would operate safely. These requirements consisted of a minimum runtime of 30 minutes, various electrical protections for components for overvoltage, polarity protection, and an emergency stop button. These were all verified with either an inspection or a test. All of these requirements were passed.
Overall, with the mechanical, electrical, and software modifications done to the car, this product was able to perform all of its intended functions. Some of the requirements that drove the main design of this robot were the position tracking requirements as well as the multifunctionality. This was so that it could be adapted to whatever is needed for the future of autonomous vehicle safety analysis. All of these requirements have been tested and verified. We believe that all of the problems that we encountered could have been avoided simply by having a more experienced engineer do the project. However, we believe that this was a great learning experience, and we are grateful for the opportunity that TES and the U of A has given us to experience a real engineering challenge and put our skills to the test.